Hi, my name is Yunhao Ge. Today, I will present our work, Pose Augmentation, a class-agnostic object pose transformation. This work was done with Jiaping Zhao and Lauren Iti. Object pose increase intra-class variance, which makes the 2D object recognition harder. To render a classifier robust to pose variance, a common method is collecting all poses of the object and creating a pose balance dataset. However, it is hard and expensive. Here, we propose a different approach. 2D images can be seen as samples of 3D pose along yaw and pitch axes. We propose a class-agnostic object pose transformation network (OPTNet) to imitate the 3D pose transformation along these two axes. So given any single pose image, we can rotate the object along yaw and pitch axes to any target pose. Instead of directly rotate pose continuously, we start with a discrete transformation, which is easier to constrain. Here, we use sample discrete pose along yaw and pitch axes as our predefined poses. We treat different poses as different domains, so that discrete pose transformation can be seen as image-to-image translation task, where a generative model may be helpful. Two-domain transformation GANs like cycle GAN have a high cost, because we should train specific GANs for all pairs of poses. Star GAN perform a method of multiple domain mapping with one generator. However, pose transformation creates a large, nonlinear spatial change between input and output images. The traditional structure of the generator has few shared structures which satisfies all randomly paired pose transformation. It makes star GAN training hard to converge. To solve this problem, our OPTNet uses the eliminate add structure, which first transforms the input image into a canonical space with pose invariant representation and then transform it into target domain. The synthesis pose can increase the accuracy of object recognition. Our pose augmentation is class agnostic and can generalize to new classes. The green-framed poses are not defined in training, which shows continuous transformation. Generally, the proposed OPTNet consists of an eliminate add structure generator, a discriminator, and a pose eliminate module. Basically, the generator transforms an input pose X into a target pose Y conditioned on the target pose label C. The eliminate part tries to explicitly disentangle pose from object identity to eliminate the pose information and turn it into a canonical space. Given an input image, we randomly select the target yaw and pitch value as target pose. We do not input target pose along with input image. Instead, in the eliminate part, convolutional regularization is first used to implicitly regularize the representation to keep only the key identity information that may be helpful to any target pose, like appearance, color, and shape, and eliminates useless information which may hinder transformation, like pose. At the same time, the pose eliminate module explicitly forces the representation to contain as little pose information as possible by predicting equal probability for every pose. After that, we add the target pose as a mask vector and synthesize the target pose. The discriminator leveraging pose classification and image quality classification to supervise optimization of transformation. There are two adversarial learning frameworks. First, the whole eliminate add generator and discriminator, which try to synthesize correct target pose with high quality. Second, the pose eliminate module can be treated as a special discriminator, which form an adversarial learning framework with the eliminate part of the generator and try to eliminate the pose information in canonical space. During training, G first mapped the original pose image to target pose and synthesizes a fake image. Then, G tries to reconstruct the original pose image from the fake image given the original pose information. We use the cycle consistent loss to optimize G. After discrete pose transformation converge, we make the pose representation continuous and normalize the continuous transformation process. There are two main changes. First, we design a two-dimensional linear space to represent pitch and yaw values. Discrete poses are represented as integers, and we could interpolate and achieve continuous pose representation. Second, we randomly sample decimal pose as target pose and use the style consistent loss to regularize the synthesis image, keep pose representation consistent along 3D axis. Overall, The loss function contains three groups: multi-domain translation loss, pose element loss, and style consistency loss. To explore the performance of OPTNet as a generative model to help the training of a discriminative model, we design object recognition experiments. We use a subset of large pose balance dataset iLab 20 million. Different training sets are tailored from iLab 20 million. In pose unbalanced PUB, 5 classes of vehicles have all 6 pose images, while the other 5 classes have only 2 pose, which has significant pose bias. In pose balanced PB, each category among 10 classes of vehicles have all 6 pose images. There is no pose bias. We first train OPTNet on pose unbalanced set to learn the object transformation ability. Then we use the trained OPTNet to synthesize the missing 4 poses in PUB and form a synthesis pose balance training set SPB. To show performance of continuous transformation, we also interpolate pose values and synthesize 5 new poses beyond the predefined ones, and form a synthesis additional pose balance training set SAPB. We also form APUB using common data augmentation method. All training sets are used to train the same classification model from scratch and to calculate the text accuracy on the test set. The original gap due to pose missing is nearly 7%. OPTNet fills this gap, which shows the synthesis missing pose image can improve the performance of object recognition. Specifically, the pose vacant category shows significant improvement in accuracy. The comparison of SPB and APUB shows our pose augmentation is better than traditional augmentation. Because OPTNet can continually synthesize interpolation new poses, SAPB performs even better than the PB set, achieving highest improvement. OPTNet can transform pose on different classes of vehicles simultaneously. It shows the class-agnostic transformation property. We further verify on other dataset, RGBD dataset. For each class, we only use around 100 images for each pose to fine-tune pre-trained OPTNet. Performance shows pre-trained OPTNet can generalize well to RGBD dataset, which demonstrates that OPTNet is a class-agnostic object pose transformation framework. Similar to iLab 20 million, we split RGBD into a pose balanced and pose unbalanced training set. The accuracy improvement demonstrates that our pre-trained OPTNet can be generalized to different datasets and boost the discriminative model in object recognition. Because the accuracy improvement in RGBD is smaller than in iLab 20 million. Indeed, maybe distinguishing a yellow sponge and a black keyboard can easily be achieved by size or color even without pose analysis. So we want to explore the object pose significance in different object recognition tasks. We first make the classification harder by selecting the top 6 categories which are more confused by classifier. We then assign different fixed pose to each category to improve overall pose variance. We have 2 conclusions from the result. First, when the interclass variance is small, pose balance is more important because OPTNet can improve more accuracy after synthesizing the missing pose. Second, when class variance is fixed, the more pose bias we have, the more accuracy improvement we will get with the help of our pose augmentation. We directly use the pre-trained OPTNet on iLab 20 million to do pose augmentation on ImageNet without any fine-tuning. The general shape and pose structure of synthesis pose are reasonable. Here, we show more results about OPTNet. If you want to learn more about our work, please visit the following links. Thanks.